So, welcome everyone, those present in person and also online on YouTube. So, it's a great pleasure to hold this Infosys Prize lecture by Professor Arindam Ghosh from IIC. So, to start off the proceedings, I'll hand over the mic to Professor Rajesh Kupakumar for the welcome note.
Thanks, Shubro, and my welcome as well, both to people here and in the virtual mode. Just for the sake of many of the people, especially the ones who are joining by Zoom, let me just say what ICTS is, a few words about ICTS before we hand over to the speaker today. So firstly, I'm very happy that the Infosys Science Foundation has partnered with us for this Infosys Science lecture. This is, I think, the second such science lecture we had here. We earlier had one by Professor Nalini Anantharaman as well. ICTS is the International Center for Theoretical Sciences. It's a part of the Tata Institute of Fundamental Research, and we have sort of a threefold mandate of research, programs, and outreach. Research at ICTS is across many disciplines in theoretical sciences, in particular in the mathematical sciences, physical sciences, and now also in computer science. We have a graduate student program. So for young people, this is a place I would encourage people to consider for their PhD, because as a PhD student, you'll get a unique opportunity to interact with people not only at ICTS, but from around the world, thanks to the second component of our mandate, which are the programs. And we have programs almost throughout the year, and they are organized by people from around the world. And there's a definite program approval system, and you can put, any set of scientists can put in a proposal for a program at ICTS, and we've had a packed schedule of such meetings. And now, after COVID, we are back in person mode, and you can follow us on YouTube, where all the lectures are put up, and also in many of the live stream, many lectures are also live streamed like this one. So, and finally, we do a lot of outreach as well in terms of public science communication and also science pedagogy with something called the math circles as one of our latest innovations, where we are trying to identify, nurture mathematical talent from grades 7 to 9. And at the moment, that's working in an online mode. If you're interested in finding out more about it, please visit the ICTS outreach webpage and look for math circles there. So that's just a little bit about ICTS, probably boring many of you who are from ICTS, but so let me hand it over to Shubro to introduce our speaker, Professor Arindam Ghosh. I'm very happy that Arindam is here. He's been here for many of our meetings and so on, and it's a nice occasion to have him back at ICTS. So Shubro will formally introduce.
Thank you, Rajesh. So let me now move on to the next part. I'll first read out a message from the Infosys Science Foundation and then introduce a speaker. So the message from the Infosys Science Foundation first. The Infosys Science Foundation was established in 2009 with the stated purpose of elevating the prestige of research in India. The foundation gives the Infosys Prize for path-breaking research by Indian researchers. In addition to the prize, the foundation aims to disseminate scientific knowledge and collaborate with institutions as a part of its objective to inspire young scholars and researchers. The Infosys Prize lecture series is a way for the prize laureates to communicate their work to a wider audience and spark conversations around their work. The laureate, Professor Arindam Ghosh, is the winner of the Infosys Prize in Physical Sciences in 2020 Professor Ghosh is a professor of physics in the Indian Institute of Science, Bangalore. He was awarded for his development of atomically thin two-dimensional semiconductors to build a new generation of functional electronic, thermoelectric, and opto-electronic devices. So that's the end of the message. So I'll now introduce the speaker. So it's my distinct pleasure to introduce Professor Arindam Ghosh from IISc for this Infosys Prize lecture. Professor Ghosh and his group is known worldwide for their research in novel phases of electrons. And in particular, his research has focused on transport, thermoelectric, and optoelectronic properties of two-dimensional materials, such as semiconductors, few layers of graphene, and magnetic nanostructures, amongst other things. So the electronic properties of materials form the basis of our technology, and this technology stems from what these electrons do, many electrons do inside these materials. And amazingly, this field throws up lots of questions about basic sciences, cutting across the board, starting with condensed matter physics to material sciences, to various aspects of quantum field theory, as well as branches of mathematics. And while the electrons in these materials themselves are the same, these different materials provide different platforms to bring out different collective properties, which then form the basic fundamental building blocks of the technology. So Professor Ghosh's research addresses all these various aspects of electronic properties, starting with the basic building blocks all the way up to their potential applications, something that we will hear today from his talk. And his work has been widely recognized by the community and has fueled a lot of subsequent research. And the long list of awards that he has received bears testimony to this. And I'd like to particularly mention the Shanti Swarup Bhatnagar Award, the BM Birla Science Prize, and of course the 2020 Infosys Prize in Physical Sciences. And we are very happy to have him giving the Infosys Prize lecture today. So, Arindam.
Okay, Shubhra, do I stand there or?
No, you are.
Okay. Shall we start? Okay, good. Thank you, Shubhra. At first, I would like to thank the Infosys Science Foundation for this prize in the first place. And it's nice to talk about the work that was recognized by the community. I would also like to thank ICTS, Professor Rajesh Gopakumar, as well as Shubhra for hosting me here. Although the topic of this talk is more general than the theoretical sciences that's being practiced here, and all my previous visits here had been far more fundamental than what's going to be today. But I still thought we should go ahead with it, because even if the talk is in ICTS, because today the faint boundary or the artificial boundary that we create between theory, experiment, and various other branches or the activities in science is slowly blurring. So what I would like to do is give you an application and try to say, okay, this is where the theorists can come in and collaborate and produce something which is tangible and make a difference to social life, actually, in general. So my talk will be building technologies, and the building technologies with 2D systems, and the 2D system started with graphite. I wouldn't say 2D system started in terms of understanding, but 2D system started for application purposes with graphite, and the layer of that is graphene that we all fairly, I'm sure, know about it. The reason graphene became interesting is because the layers between two graphene layers in graphite, the interaction is 100 to 1,000 times weaker than the standard solids, which are bonded covalently or ionically in many other solids. So this is why you can easily exfoliate a layer of graphene, which are from the mother solid of graphite. Okay, so, but we all know when it started, but actually the effort to separate graphene from graphite started quite a while ago. Actually, it's in the mid-90s, where there had been chunks of graphite, which people tried to scrape off from the mother solid to create a single layer. You can see this is a paper which was in 1999, I think. And then, there are papers from, this is from the Washington, this is from Harvard group. So they all tried to create a chunk of graphite and then try to press it with an atomic force microscope in the cryogenic atmosphere. And they did fantastic jobs actually to take the whole thing in the cryogenic temperature, dip it inside, and it's a huge operation. There are people who are doing chemically as well. We're trying to take graphite and put atoms in there and then try to agitate or shake it very heavily and then take it, take the individual layers out. So there are many things that was being tried. But at the end of the day, it all turned out to be far, far easier than what people thought it would be. And not too long after, that is in 2000, this paper came out in Science, and now it's, I think, crossed 66,000 citations, which showed that a much easier job will be to simply take a Scotch tape and take it out of graphite and press it on a silicon oxide substrate. That gives you a perfectly single layer, single crystalline piece of a two-dimensional crystal. So for that, of course, these two gentlemen, Andre Geim and Kirsten Novoselem, got the Nobel Prize in 2010. And the way they got it is very simple. They took a substrate which is made of silicon oxide, and with a doped silicon, which is like a metal, it likes as a metal electrode, then take a piece of Scotch tape, which is sticking a little bit of graphite on it, and you press it, and then you discard the Scotch tape, and you are left with something which is a single layer of graphite on a silicon oxide substrate. Then you take the electron beam lithography, and then that sort of gives you the field effect transistor, which is how the field of 2D started in the first place in 2004. Well, I have to say this because that's roughly when I joined IIC as a faculty member. And this was something which was very good because it's so simple and it's so cheap. Particularly because you see, when I joined, this red one is the GDP, or the fraction of GDP that goes into the research in India. This is the data taken from the Department of Science and Technology, so they can't contradict me. So I joined somewhere here, 2005, 2006. And as soon as I joined, the government started reducing the GDP ratio fraction. And so there was very little money. And in addition to that, in India, doing experiments is something which is, you have to deal with certain dichotomy. For example, we now have fantastic, we started, at least at the time when we joined, we had fantastic facilities, a clean room, you could make devices with, in the lab, but at the same time, we used to deal with infrastructural disasters. For example, one day you come to the lab and find the liquid nitrogen container is lying on the ground because the base has been too soft and the whole thing fell down, and so no experiments for the next 2 months. So you have to deal with this and then find out the best way of getting your work done. And graphene devices were actually very, very good because you could make many, you didn't have to import them. So you have that in the lab, you have plenty of graphite you can easily get access to. So we started with this direction and tried to understand what kind of new physics we could do. So the graphene physics itself started with 1947-ish with this gentleman, Philip Wallace, a Canadian scientist, who solves the problem of graphene in a solid which is two-dimensional hexagonal oriented. So, and I wouldn't go too detailed in it because most of the people already know about. So essentially the idea here is that the low energy bands in this kind of a lattice is something which looks like a linear dispersion with energy, where each points on the Brillouin zone has got a cone, and as a result, you have the conduction band and valence band. Conduction band is completely empty, and valence band is filled. It's like a zero band gap semiconductor or semi-metal. And in addition to that, the electrons behave like photons in graphene, but of course with a much smaller velocity than light, about 300 times smaller. So this led to a lot of activities, and one of the immediate effect of this conical band structure was expected to be very, very fast electrons in graphene. So if you ask for the technology, or if you ask for the entry of graphene into the domain of 2D, it started with the notion that graphene will someday be so fast that we can make high frequency transistors that power our laptops or electronic gadgets, and so on and so forth. So let me give you a little bit of understanding what was the motivation at that point of time. This is a typical field effect transistor that we all have in our electronic devices, where you have a source and a drain which punches electron in and takes electron out. And there is a gate somewhere here, which is a metal. And if you put an electric field on the gate, it changes the current that is going through from the source and the drain. A typical graphene device works exactly the same way. There's no difference whatsoever, in which you have a gate, which is this is the big doped metal, which is underneath. And then you have got a layer of channel, which is graphene, which is like an channel through which the electron flows. And these are source and drain electric fields. So if I measure the electrical conduction in graphene, that is the conductivity of the metal from here to here, and where the gate voltage, the voltage you put on this doped silicon, changes the electron density, then depending upon where the graphene is sitting, the conductivity shows a behavior, something like this, which is called an inverted bell type structure. This is the part which is doped with electron, and this is the part which is doped with holes. And if I take the conductivity is equal to the electronic charge multiplied by the density multiplied by the electrical mobility, what happens is, in the case of graphene, the electrical mobility can be very, very high, nearly 10 power 5 to the 6 centimeter per volt second, which is approximately 4 orders of magnitude larger than typical electronic devices that we have. The silicon devices have got typical mobility values, which is in the order of few hundreds or so. So that's great. The reason that's great is because now the electron can move really, really fast from one end of the sample to the other, which means I can now create devices that can work at very high frequency. So the first application was intended to be in high frequency electronics, and that led to actually some initial results. Also, by then you can see this is the frequency at which an electrical transistor can work. And this is the length of the gate. That means the distance the electron has to travel from one end to the other. And you can see in the case of graphene, you can actually have extremely fast transistors. And the expectation is someday we will have a terahertz frequency electrical transistor using graphene as an electrode, which is why very fast, not the logic devices, but at least the communication devices can, in principle, work with a graphene type of field effect transistors. Okay, but I'll give you another example, which is a fun example. Because in addition to the mobility, the graphene has this unique semi-metallic structure. Can we use that? And I'll give you an example of what you call a technology application, which is in adaptive camouflage. Very important if you are in battlefield. Okay, suppose you have a soldier whom you want to vanish somehow. How would you do that? So, you know, the way we see others, even in the infrared camera, of course, imagine you are in nighttime, there's no visible light. So the way you image is using infrared cameras. And these infrared cameras, particularly at room temperature, essentially captures photons which are in the order of 10 micron-ish. That means about 0.1 electron volts, right? So the idea is, suppose you have a material which, for example, our clothes, it captures those photons and re-emits them, then you can see that cloth. But suppose you have a cloth that captures them but doesn't emit, then you are vanished. So imagine you have a graphene, which has a conical band structure like this. So if I do not dope at all, then lights of this energy can come and the electrons can be absorbed and graphene will re-emit and you can see the cloth. Now, if I dope it and there is no state available because these states are already occupied, the transition cannot take place, which means that the light cannot be absorbed or re-emitted. As a result, by having a cloth, which is like a doped graphene, you can stop the infrared radiation to be absorbed or re-emitted. And this can be demonstrated. You can see that this is a graphene-based system, and you can apply a little bit of electrical voltage to dope it, and you can see the hand has disappeared because the hand does not, the infrared radiation that has been emitted by the hand is not being absorbed or being re-emitted. So this is one of the applications. I thought it's fun application because it depends on the semi-metallic behavior of the graphene band structure. But since then, we learned a lot about graphene. Okay, for example, we know that it can be used as high-frequency transistor. It is extremely high. It is the highest thermal conductivity material because of the strong sp2 hybridization between two carbon atoms. It is the highest thermal conductivity that we know today, even 5 times more than silver or gold or something of that sort. It has got such a high surface area because if you take graphene out one layer and you calculate the surface area that you have got per unit per weight, it is the highest known because it's, of course, the thinnest material that we know. And as a result, batteries are extremely important for such kind of applications. It's the strongest material that we know. As a result, ballistics, concrete, these are systems which can get hugely benefited. I'll come to that in a minute because we see fantastic buildings, how you can make long-lasting, stronger, etc. We have nearly 98% transparency, which means it can have solar cell applications. And also, it's nearly impermeable to gas. And as a result, you have got waterproofing, barrier properties, and there's a huge number of applications that can have. Of course, in addition, must not be undermining the application of graphene in fundamentals. A little bit was said at the beginning. Graphene's entry was immediately associated with this new type of Hall effect, came in through two-dimensional Dirac fermions, and led to a very distinct set of Landau levels, and which is now has become like an iconic example of quantum Hall systems in graphene Dirac fermions. Then after quantum Hall effect, we started topological effects in graphene. For example, one of the major directions in graphene is to create grain boundaries. For example, the grain boundaries could be in bilayer graphene. You can see that if the bilayer stacking order, which is AB to BA, where which carbon atom is sitting on which layer, if that can be reversed, it can lead to topological states along the grain boundary and non-dissipative transport. Many people have looked at various aspects of it. For example, you can apply a potential from, say, boron nitride or some other material, and lead to inversion symmetry breaking of the graphene lattice. That leads to another set of different topological state. People have looked at it from electrostatically driven by applying two opposite electric fields. Also, it has led to inversion symmetry breaking and new topological phenomena. Again, these are the things which I'm not going to be talking about, but we will look at what kind of application, because this science has now been looked at quite extensively over the last decade or so. The latest kid in the block, of course, is the Coulomb interaction effects, and which has led to superconductivity, maybe, where you now have, instead of one layer graphene, you have got two layers. But now, with our ability to put them together, we can put them in a slight angular mismatch, through which you can engineer band structures where the electrical bands are extremely flat, and that leads to a completely new set of physics. For example, it leads to strong insulating phases at certain filling of these bands, and that's called the Mott. Those are supposed to be Mott insulating phases. And right next to Mott insulating phases, there had been discovery of superconductivity, and there is a huge debate where the superconductivity comes from, whether it's electron phonon induced superconductivity or whether it is superconductivity driven by the Coulomb interaction. Recently, we have looked at these kind of directions as well, and we find that there is a very strong non-Fermi liquid behavior and the strange metallic behavior in this region where the superconductivity has been observed. It's still a very open field, and it's a very new field, and lots of work happening to understand the complexity of the phase diagram simply because it comes as an interplay of strong Coulomb interaction as well as the angular mismatch between two graphene layers. So with this, I would like to say that, okay, all these things are going on in graphene, but in parallel, there had been another class of compounds that was coming up. And molybdenum disulfide was a beautiful example of how the idea of exfoliating graphene from its mother solid graphite led to the whole new activity of this field, which led to the discovery of again, a field effect device made from this another material called molybdenum disulfide. Molybdenum disulfide is very similar to graphene, except for the fact that it doesn't have carbon. In terms of structure, if you look at from the top of it, it is a beautiful hexagonal crystal. And this is molybdenum, this is sulfur. And then the Brillouin zone is also very similar, which is like a K and K prime have something like a hexagonal structure. However, there's a key difference between the molybdenum disulfide and graphene is that this guy has a band gap. See, graphene doesn't have a band gap, but this one has a band gap of about 1.9 electron volt, which leads to a single layer semiconductor that we never had before. For the first time now, we have a beautiful semiconductor with which we can make devices and overcome certain difficulties that we had in the case of graphene. So this is our work long time back, about a few months after the original paper on molybdenum disulfide came out. You can see that as you change now the gate voltage, the electrical conductance changes by orders of magnitude. Instead of graphene changes by a factor of 10 or so. That's because graphene doesn't have a band gap, and now you have a band gap to completely switch the system off. It led to a very interesting solution to the electronic problem that we have today. There is, as we get smaller and smaller, transistors for more and more memory, more and more computing capabilities, one of the key problems that come out is what is called a short channel effect. A short channel effect is nothing but when the distance between the source and drain is shrunk to the size of the width of the current carrying channel or the depletion width, it leads to a lot of problems. And one of the problems, for example, is drain-induced barrier lowering, which means that even if you try to switch the transistor off, that means when you switch your laptop off, it still consumes electricity. And you don't want that. You want to make the transistor to be completely switched off. Otherwise, you spend a lot of energy in simply running all your electronic devices. So today, short channel effect is one of the most important problems in shrinking of the electronic industry. So this problem was immediately sorted out by the, this advent of this atomically thin semiconductors, because now we could go to the thinnest possible channel, and hence the short channel effect was automatically suppressed. So this is something which is another huge technological impact, which there is a lot of wafer scale synthesis of this kind of material is now being sought after. Okay, then in addition to that, there was something new that started, and that is called, because these are semiconductors at the surface, when you shine light, you find that there is a change in electrical current, and that was the start of 2D optoelectronics. This is one of the biggest fields in the materials industry today, where you can shine light to change the current, and that essentially means that you have a new generation or a new platform of devices that can be used in cameras. And the question is, are they better than the existing technology, so that we can try to see how we can take advantage of that. There's a lot of new materials now. I will not spend much time. After chalcogenized, even the high temperature superconductors have been exfoliated, and there have been devices made from them. In principle, there are about possibly 1,825 different compounds that in principle should be possible to exfoliate. Okay, so there's a huge phase space to deal with. However, when all these things were going on, there was one question that we started asking, and that is, okay, so far we have looked at individual materials. We have looked at graphene, we have looked at molybdenum disulfide, and there are other new materials that are coming up. The question is that, is it possible to put them together? and come up with something new, whether there's a possibility of emergence of some form. So this is an statement of Aristotle, which was translated early in 20th century. So the question is that what can we do, or what can we achieve by putting these unique materials of completely different chemical genre to come together? Does it lead to something completely new? So while Manchester University, the graphene was being heavily investigated, they developed it. EPFL developed molybdenum disulfide. We at the Indian Institute of Science, way back in 2012, started to put them together. And we found at that point of time that, okay, if you put them together, it's not just the addition of two materials, it's not just a heat, but it comes out to be something completely different. We showed for the first time that when two 2D materials of different origin come together, something new happens, which was not expected in either of the components earlier. So that's the emergent properties. Okay. In order to do that, we came up, or actually we followed a technique which is called the van der Waals heterostructuring, where you take materials and start putting on top of each other at any layer or any sequence that you want. Okay, so here is an example in which you just take layers of graphene, then a layer of boron nitride, then a layer of another graphene, and then you put the whole thing on top of a molybdenum disulfide layer and make a stack. So this is essentially like an artificial structure where completely different chemical or different solids come together, and you ask the question, okay, what does this new solid look like, and what kind of functionality, what kind of performance this new solid gives? Of course, the order of stacking will be entirely dependent on what kind of application you have in mind. Everything is very easy, and well, it's not easy to make, but it's infrastructurally far easier. Okay, all you need is a microscope and look at it, how it goes on. So let me show you how.
I have a quick question. Sure. With the Moiré physics in mind. I mean, how do you know about the relative orientation of each of these layers in the sort of schematic that you show?
Okay, good question. There is no unique technique, but different structures have got different manifestations. For example, if you take a Moiré physics of 2 graphene, then the best way to do it would be to look at the magnetotransport, in which the Moiré lattice gives you an additional lattice and its own structure of electronic filling. So you can do quantum Hall physics to identify what the angle is. There's a little bit of Raman spectroscopy that can also be done, but best way to identify the angle is through quantum Hall effect. But if you look at the molybdenum disulfide and TM transition metal dichalcogenides, there the technique to identify the angle will be completely different, because they're semiconductors. They cannot be, the electrical conduction is not there. So there you use second harmonic generation and other techniques to know the angle. Sorry,
you are, but what I was trying to ask is that when you make these devices, so if you make like 3 or 4 devices, is the orientation, relative orientation, really is similar or same in these devices, or the different, and then they reflect in the properties? We don't have actually now as we learn more and more, the yield is getting better. At this point of time, if you aim for say 1 degree misorientation, it can easily be something around 1.2 to 1 or 0.8 or something of that sort. But now we have techniques in which we have stabilizing layers of some form, so that can give you better accurate, So when we make it, we do it purely mechanically, but then we characterize them using transport. So the yield, I would say about 20 to 30% of what you want and what comes out. All right. So here is a way I can show you how to make such a device. So for example, I want to make this 4-layer structure. For example, graphene, TMDC, that is molybdenum disulfide, another layer of graphene and boron nitride at the end. You took out the graphene first, then we identified a layer of TMDC. You can see you can turn it around, and then when you're happy with the orientation, and then you essentially pick the whole thing up now. So these two will come up, and there's a layer of graphene and a TMDC layer, or the molybdenum disulfide layer.
Then we try to find another graphene layer. And this is, for example, there is a graphene somewhere here. So which then what we did, we essentially put that old stack on this new graphene layer. Now we have got 3 layers, one graphene TMDC layer, and you can see 3 here. And finally, the big boron nitride chunk, what we will do is take these 3 and we will put that whole thing on this boron nitride, and we will end up with 4-layer stack in the laboratory. So this is how we create such van der Waals heterostructures in the group. It's actually very interesting because you are actually taking out one atomic layer and putting it where you want, which is not easy. And then we put them on a substrate where you would like to make the electrical leads, et cetera, and make a device out of it. Yeah.
The interlayer bonding is still like in graphene?
Absolutely, it's van der Waals interaction. Yeah, so this is one of the advantages. These, not just the interaction is van der Waals, but also in spite of making in such crude ways, it turns out that the interface is almost always atomically clean. And you don't see junk in the between two. And so you can actually look at the physics of interfaces through these in quite easy way. Okay, so there are many van der Waals stacks. This is a 2-layer stack, this is 3-layer stack, 4-layer. You can make all sorts of very interesting stacks and look at different physics and device abilities. The one which I'm going to talk about, because this is a part of our Infosys prize as well, so I thought I'll spend a couple of minutes here. So for example, here it's much simpler. We just took out a graphene layer, and put it on MOS2 so that we make a new kind of van der Waals, a bicomponent van der Waals heterostructure, which is based on graphene on a layer of transition metal dichalcogenide, which is a semiconductor. Okay, and what we do is that we put electrical contacts such that we look at the electrical current through this when the whole system is illuminated with optics. So this was the first experiment in which we looked at this hybrid structure in the presence of optical excitation. Okay, so this is how the schematic is. So you can see the graphene and the molybdenum disulfide underneath, and electrical conduction through graphene is measured when the system is illuminated by some optical radiation. Okay, now what happens is very interesting. This is experimental data. You can see when the light is switched on, the current through graphene immediately drops to a very large number by about 30 microampere. And then when the light is switched off, it returns almost fully, but then you give a little bit of a voltage pulse on the gate to get it back to original value of it. Now this is very important. This essentially is a conversion of light into electricity. The light comes and the change in current takes place. So, and this can go on forever as long as you keep on repeating this cycle. What was interesting in this was the following, that the change in current was extremely large for a tiny amount of power of light. And if I look at the number, essentially ampere is the change in current, watt is the amount of power that you shine, and this number gamma is called a responsivity, and that went to 10 to the power of 10 ampere per watt, which for a simple silicon or what we have in the laptops is about 1. So we obtained with this new hybrid structure, we obtained about a 10 orders of magnitude increase in the optical responsivity of a hybrid structure like this. So we understood that over the years, we understood the basic idea here was nothing but, molybdenum disulfide acts as an absorber layer. As soon as the light comes, it creates an electron hole pair, and then the electron goes into graphene and forms, goes back and along the circuit, leads to the current, and the hole remains trapped here. There's an optical gain involved that leads to extremely high responsivity. Okay, so that's the physics. But if you look at the technology of optoelectronics today, these are various materials. This is silicon, this is organic photodetectors, this is plasmonics. This is now the most sensitive optoelectronic element that we have in the world. And if you see the number is that in the order of 10 to the power of 9, 10 to the 10 ampere per watt, means if I can see a change of current of 1 nanoampere, we should be able to detect change in energy of the order 10 to the power of minus 19 watt. 10 power of minus 19 watt is a very small energy. It is typically an energy of a single photon. It's also roughly the energy that goes through a 1 square meter area from a candlelight about 1/3 the way to the moon. So it's extremely small energy. And because it can detect, or its order is in the order of a photon, the next natural question that we asked is that, okay, can one detect single photons with two-dimensional hybrid? Again, the reason behind asking this question is now we move to a new technology domain altogether, that whether now we can use these systems in the emergent quantum technologies. So I'll take 1 minute off here and say what kind of applications that quantum technologies can see of this kind of hybrids.
So you mean optical photons?
It's optical photons, correct, absolutely. Although now we are moving into infrared photons as well. So let me tell you a little bit about quantum technologies here, and I connect to what we have done earlier so far. So we all know that quantum technologies is something which is extremely becoming really, really important now. There's 15 countries have got their own quantum missions, India being one. And this, as of 2020, there have been 22 billion of investments in this technology. It promises us with new type of clocks, simulators, sensors for various purposes, for strategic purposes as well. We have medical imaging, diagnostics. We also have quantum key distribution, there's quantum secured transfer of information, and of course, nothing but, we shouldn't miss out the component, which is quantum computation. And in many of these applications, single photon detection plays an extremely important role. For example, of course, communication. In any case, communication, if you've got from the source to the receiver, in order to know the basis in which the single photons have been transmitted, you will need single photon detections or an interferometer. So single photon detection is an extremely important aspect of communication. In the case of computation as well, there are many, particularly with photonic quantum processes, in which you demonstrate quantum advantage. For example, this is an example of a boson sampling activity system in which you have got interferometers, and you shine single photons and then let them interfere, and eventually they are detected through the single photon detectors on the other side. Given the size of this interferometer, it can be considered as a classically hard problem, and it has been used to demonstrate quantum advantage with the photonic circuit. And what you need in such cases are detectors which can detect the number of photons that actually arrive in a pulse. And that's not very easy. We are not talking about just single photon detectors. We are asking for detectors in which when the light comes and falls, you would know exactly how many photons are contained in those pulses. So that's extremely important if you want to do photonics or photonic-based quantum computation. Of course, the sensing and metrology, it's natural that you would need a very high quality single photon detectors. For example, the quantum radar, in which you create an entangled pair of photons, one becomes a signal, other is the idler, and then the signal essentially gets reflected by the object, it comes back, and then you correlate the signal and the idler, and through that, you can look at signals which are buried in a large amount of noise. So that's one of the directions in which quantum imaging will be taking, and using single photon detection as the key platform. Okay, so what's the present technology for the single photon detection today? There are primarily 3 directions, and all have got certain problems. For example, if you've got a single photon multiplier, it can work at room temperature, which is very good. But it has got very low frequency efficiency at telecom wavelengths. Telecom wavelengths are the most important ones when you apply single photon, because you need information processing through fiber optic cables, which works at 1550 nanometer wavelengths. And of course, there are very large voltages with a very bulky system. It's very difficult to work with. We have got avalanche diodes, which are essentially semiconductor diodes, which means that now you can use silicon or low bandgap semiconductors like indium gallium arsenide as the platform. These are good because these have got high efficiency at the telecom wavelength, easier to handle, but they often do not have the number resolving properties. That means you need a photon, you need a detector which will tell you how many photons you have, but these are difficult in that way to resolve the number of photons in a pulse. But they have got slightly better, operating temperature, more convenient, 200 to 300 K, you can still operate them. The most popular ones are actually superconductor-based ones. So these are superconducting single photon detectors, in which there are two types of detectors primarily. One is the transition edge sensors, other is single photon nanowire sensors. These guys have got extremely high efficiency. The problem is the transition edge sensors have got number resolving power. It can detect how many photons are there, but they're very slow. They're just about 100 kilohertz. You need fast detections. You need gigahertz based. But that is availed through the nanowires. How the nanowire detectors work is very interesting. So they have got a superconducting nanowire, and you shine light, it gets absorbed and it gets heated up locally. The moment it gets heated up, it becomes normal because it's a superconductor. And the normal region essentially makes the supercurrent goes around it, right? And that increases the current density. And the moment the current density increases, it becomes normal, and the whole system then becomes non-superconducting or normal. And then you detect single photons in that manner. The problem with these is that these are low operating temperature, almost always working below 4 Kelvin. The TES, these detectors work even below 100 millikelvin. So these are difficult detectors that way in terms of portability. So everything have got a little bit of a problem. So what we wanted to do is, by the way, even then, look at the kind of market now. You can see since 2019, the number of SNSPD systems. We ourselves bought 2 of them recently from recent research grants. So there's a huge opportunity here to look at alternative systems which can overcome certain difficulties in the existing devices that are used. Because of the quantum technology coming in, these kind of systems are becoming more and more popular and becoming common in many quantum computation and communication laboratories. So we have now looked at this, and we found that even because of the sensitivity of this new 2D heterostructures, these systems are quite useful for this single photon detection. We have demonstrated single photon detection. This is a 4-layer structure. This is more complex than just graphene and molybdenum disulfide, but here we have reduced the dark current by looking at gapped bilayer graphene. But look at the overall performance. If this is a pulse of light, the current immediately drops, and these subsequent pulses, different size of the drops, which you can make a histogram from, and you can see the single photon detection for various average power of excitation. You can see that the number of photons in a pulse can be quantized. 1, 2, 3. This is the effective number of photons in a pulse. And by changing the power of light that is falling on the heterostructure, you can see that 2 photon pulses are more than single photon pulses. 3 photon pulses pick up, and you can actually make this individual single photon detectors or number resolving photon detectors using these heterostructures. Why are we excited? Because you see, in the case of graphene to molybdenum disulfide, the charge transfer takes place in few picoseconds, much faster than the thermalization of a single photon nanowires, single photon detectors based on superconducting systems. This can operate at room temperature. We have looked at room temperature performance of these detectors. The challenges are now one has to integrate these with silicon photonics. It needs to be increased. The efficiency needs to be increased, but those are hopefully solvable engineering issues. So we are quite optimistic that we should be able to make new kind of detectors for single photons for quantum technologies. All right, for our current group activities, I told you a lot of light matter interaction. We are strongly interested in the topological phases. We are interested in charge and energy transfer across various 2-dimensional layers. And last but not least, we're also trying to see how these kind of heterostructures can be utilized in mimicking certain biological systems, particularly for neuromorphic applications. I'll give you a quick summary on that before my final phase. You see, at the end of the day, if you look at a synapse between two neurons, okay, it's like a resistive memory. It means that if I want a synapse to transfer information from one axon to the other, suppose you want the transfer of charge from here to this side and not from this neuron to this neuron, then you need to either make it electrically conductive or electrically resistive. Suppose this neuron is firing first, then this one, which means you want, that is the causal relationship. You want the neurons this neuron to fire first, this neuron to fire next. In that case, you want this synapse to be electrically conductive. Suppose there's a problem, and for some reason this neuron is firing first, which you don't want, then you want to make this synapse to be non-conducting, and hence you want its electrical conductivity to go down. So it is this neuron gives you first pulse, then you can continuously get that, and you want this synapse conductivity to be large. But if this neuron fires first, you get opposite pulses and the conductivity goes down. So effectively, a synapse is like a resistive memory, where by continuous single direction of pulse increases and the opposite increases conductivity, and the opposite pulse direction decreases the conductivity, which is called a depression. Now, using this molybdenum disulfide based transistors, we could mimic the synaptic activity quite nicely. This work has suddenly become very popular. When we did it, we didn't really think it would be interesting. We just thought it's fun. Okay, so we have a layer of molybdenum disulfide sitting on the surface, and there is a charge storage layer of graphene, which is below an insulating layer of boron nitride. The blue layer is like a dielectric, which separates the electrically conducting channel from a charge storage layer, which is graphene. So all we have done is, by applying a voltage pulse on this back gate, we either take charge from a top layer to the bottom layer and store them there, that changes the electrical conductivity, or by applying an opposite pulse, we have taken charge out of the storage layer and put it back into the top layer, that decreases the resistivity. So this is, you can see the change in potential pulses. This is the pulse applied to the bottom gate here. You can see the change in the current. If I put a negative pulse, it essentially increases the current, that because the more and more charge comes out, and that change makes this channel conducting. And if I put opposite voltage pulses, exactly opposite path of charge makes the channel more and more resistive. So it's like a memory. And we have made beautiful potentiation and depression activities for many, many cycles, and showed that this can lead to a very interesting neuromorphic device. What is interesting is that energy dissipation per pulse is actually even smaller than what human brain takes in a single memory actions, which was quite interesting, because you can operate such electronic devices in a very small conductance level. Right. How much time do I have?
5 minutes.
Okay, excellent. So I will talk about a little bit of technology roadmap before I finish. You see, what happened is we have two different directions. One is electronics, and other is infusion of bulk 2D systems into composites and various other technologies. In the case of composites, we are seeing new directions of building materials, for example, and that's going to come in the next few years, 2023, 26. By the way, this data I have taken from the Graphene flagship annual report in 2020. So this continuously is getting recalibrated. Graphene and the 2D materials is falling behind the expected timeline, but this can be taken a rough guideline at least. So we are looking at, I think it's too small from your side, but anyway, let me explain. So composites based on 2D systems are becoming more and more viable, and may be now possible to make them in certain commercial order. The energy becoming a very important direction, in which we are talking about batteries. We are talking about perovskite solar cells, and probably fuel cells in somewhere around 2030, where the material, the anode material of batteries will be made of graphene and 2D kind of a system. We have data communications, in which now the advanced optical networks can be thought about. That's already several propositions of using 2D systems for data communications, and probably down to 2030 and all 6G and other architectures possibly will have a strong 2D component in it. We have electronics, as I said in the beginning, that's how it started. We already have the low-cost printable electronics, because graphene is very thin, flexible. One can print electronic boards now with and flexible electronics, foldable papers. So those are already coming into the market in a little in phases. Hopefully by 2030, we will completely have spin logic devices based on 2D semiconductors and 2D magnetic materials like chromium iodide and various other systems. Sensors and imaging, as I showed today, the optical part, this is where we come in a strong manner, in which we are talking about imaging using graphene and 2D hybrids, where you can access a regime which is impossible to access with individual silicon and various individual components of bulk crystal. And finally, the biomedical technologies. I actually deliberately gave the neuromorphic example, because this is one direction in which there's a lot of activity going on in interfacing neural activities and 2D material, simply because of extreme sensitivity of these systems to local charge transfer. Suppose you want to take an EEG of brain. Graphene as a material is extremely sensitive to its local charging environment. So whether the charging activities of the brain can be sensed by electrical transport through 2D materials and graphene is one of the key areas of research. And hopefully there would be devices and materials. For example, in prosthetics as well, there's a strong involvement of 2D materials today. So those are the directions which probably is going to come within the next 5 to 10 years or so. Okay. There are more than 350 companies now on the graphene and this kind of structures, with a global market probably exceeding to a few $1 billion in the next few years. We have the key requirement for this is a large area synthesis. The chemical vapor deposition of 2D materials is one of the directions in which such materials can be created. Now there is 6-inch wafers available for molybdenum disulfide and transition metal dichalcogenides. Yeah. I'm almost done. So I'm just going to skip through this. For example, the liquid phase exfoliation is one of the key directions. I have an information here, how we can create this bulk materials, and liquid phase exfoliation is one of the key areas in which you put liquid of this solid of 2D materials and shake them. And by the way, graphene oxide is one of the most popular directions of making such 2D layers. And I want to say that the whole concept of graphene, although we say 1947, etc., but it actually started in the year 1859, when this gentleman, Sir Benjamin Collins Brodie from Oxford, actually found that the laminar structure of graphene oxide for the first time. There's two reasons why I showed this. First of all, this paper was published in Philosophical Transaction of Royal Society. It was received in May 12th and read on May 12th. So on the same day. Today, the editor takes 2 weeks to reject the papers. So this is something which should be taken as a lesson, that you get a paper today, you read the paper today. The second thing is very interesting, that he was very upset that everybody is using the term graphite for every compound that is carbon derived. So he started the paper saying that it's indiscriminately applied. But it's true, even not to say 1859, but it is true even today, that people are using graphene in every inclusion and trying to get some new functionality out. So this is something which one has to be very careful of. So that is why the quality control is something which is very important. This paper, by the way, was actually on guano doped graphene. Okay, so it's something which came out very recently. Okay, but the problem with graphene commercialization is the prohibitively expensive material. You see, if you look at China, and it's probably quarter of a milligram, it's $0.25 per gram, whereas this is something which makes very commercially unattractive. So there's a huge scope of innovation here, and I'll skip through this part because this is something which I had a layer of different possibilities. What is important is the graphene community or the 2D community is trying to look at this cost aspect. If you want to make new composites, you need to get the cost down below $10 a kilo. It's very interesting that I'm talking from topological physics to $10 a kilo, but this is the reality of the market today. And it's only then that our current global capacity of making 2.5 kiloton per year, and that will drive the demand to 10 kiloton a year. And when the 10 kiloton a year global capacity is reached, we will probably have the first car tire that will be infused with graphene rather than carbon black. Okay, and then probably we'll have the first graphene anode material based battery when our global capacity becomes 10 to the 5, 10 to the 6 tons a year. So that is something which leads to a new challenge to the material community, that can we find new ways of synthesizing these material which can solve many of the scaling up problems, which is essentially pulling this field back, that how we make good quality material at low cost. So this is what we have done. This is my second last slide. We found recently a method in which we have created a ultrasonic generator and a pulse laser together, leads to a very high quality of graphene and 2D materials per se. This is boron nitride, which is distinctly a new exfoliation process. And with this method, which we call OME method, we have increased the production efficiency to a factor of 2 more than the existing market. This has led to a company now with my colleagues, which we call the Quant 2D Technologies. And our goal is to create a method through which the industrial manufacturing of this 2D material can be enhanced or made more affordable and more efficient with very low environmental footprint. I'd like to stop here. I would like to thank all my students and postdocs. It's impossible. There are so many of them over the years. It's impossible to thank individually, and the work that we have done, the beautiful devices that we have made wouldn't have been possible if without their skills and continuous, being at it, the dedication. Because it's not, you can go through the entire process, and then at the last step, you might find that the device has vanished because there'd been a burning out, there'd been the whole thing get washed away in solvents, and then you start again. And this wouldn't have been possible until and unless you are at it and continuously do it over and over again till you get the right device. And these people have shown how to do it over the years, and they have all done a wonderful job, and without their dedication, it wouldn't have been possible for me to stand. We have a lot of fun, of course, and we go to different outings and have food together, and we do experiments as well. So this is my summary. See, our gadgets are responsible for 4% of the greenhouse gases. And when we have about 30 billion connected devices by 2023, we need to find an alternative technology that will make the sustainable solution. And probably the 2D enabled devices will reduce the demands of the telecom as well as datacom, leading to more sustainable solution. And finally, from device-oriented challenge, we need to create the IoT, the Internet of Things today, challenged us, saying that we need to create devices no bigger than a grain of rice that can sense, that can compute and communicate without wires and maintenance for 10 years. So we need a whole different platform for device in order to achieve anywhere near to that ambitious goal. Thank you very much.
Thank you, Arindam, for this nice talk. We would like to go to the questions, but before that, I'd request Professor Rajesh Kupakumar, the Director of ICTS, to hand over a small memento to Arindam Ghosh on behalf of ICTS.
Thank you, Rajesh. Thank you. Thank you. Thank you.
Okay, so now we are open for questions. Okay.
Thank you very much for the very interesting talk. You mentioned the costs that are quite high in graphene components. What are the main contributors to these costs? Is it material delivery? Is it energy? Do you have some estimates of life cycle assessment?
Right. Okay. So there are two aspects of the graphene application. So even the cost component is hence have got two aspects. First is if you want to make graphene electronics, then one is talking about wafer scale growth and making components of 2D, not just graphene for 2D. So there the cost component comes from the basic material itself, the device to device variations, and well, that is slowly being solved as we make wafers of very large size, 6-inch, 12-inch, and so on and so forth. The other part of the cost comes in the case of bulk infusion, where you take 2D materials and infuse them in composites. There, the cost component comes because the most of the material that you start with are rejected because you cannot convert them into single 2D layers. So, say for example, the efficiency of converting a graphene nanosheets from graphite is just about few percent. So graphene oxide is much higher, but if you leave out graphene oxide route, then just about 5% to 10%. So 90% of the material is wasted. And in addition to that, there are chemical routes which are extremely environmentally expensive. So there are various reasons why this cost component comes up. So that's one of the major reasons why we wanted to see a green and low cost physical route to make such nanosheets.
So when this cycle is running in manufacturing, what amount of energy is required? Is there an estimate per kilo of product? What is the amount of energy, megawatt, or is there such estimate?
In terms of energy for a kilo of product is difficult to say simply because one is talking about, say, if I take conventional methods of ultrasonic exfoliation, in which you just take a sonicator, you shake it at a ultrasound frequency about 40 kilohertz or so, and then essentially that makes the material disintegrate into nanosheets. Now the power requirement for that comes from the ultrasonic power, and that varies. It's hard to say, pinpoint one energy number to that.
I presume there should be some continuous cycle production manufacturing facilities that should be continuously powered, right? So right. You try to make a wafer, discard some materials all this time, all this period of time, your facilities should be powered.
Right. So there you can, okay, so if you're talking about wafer, so essentially it's very similar to what standard electronic industry looks at. For example, the raw material costs as far as silicon and molybdenum disulfide or chalcogenides are concerned, its ballpark figure will not be too different. So there you are talking about, I wouldn't say, how a foundry works. A foundry works typically each wafer would be probably a few kilowatts or something of that sort, one would say, but it's very rough number. I wouldn't be surprised if I'm off by a factor of 10.
Great talk. Thank you. Just one thought occurred to me about this. You described the neurotransmission between two neurons, actually. So do you think it can be sort of replicated to some sort of a network?
Yes, and, absolutely. So this is why we are excited by this direction. So when we did this work, we were essentially looked at just a single exfoliated layer. But now I showed the wafer scale transition metal dichalcogenate, the molybdenum disulfide, and these materials are coming up. So it is now possible to make networks of multiple large number of unit cells, each of which act as a synapse. And you can make memory circuits with this. It's all possible now.
I have one more question actually. So I mean, it's so you mentioned about the enhancement of imaging in biology, I mean, especially the brain.
Yeah.
Can you explain that a little bit more?
Sure.
And what is the qualitative jump which quantum technologies bring to that?
So one of the directions is to look at the electrical activity in the brain. So essentially, look at the electrical. At the end of the day, we are all there between pulses of charge from one neuron to the other. So the goal here is, because 2D systems are at the surface. See, unlike silicon, which is a buried surface, 2D systems, like it has a surface, it's built on the surface. So you can come very, very close to where the sample is, or where our brain is, right? So now, because of the charge reorganization in the brain, it is possible that this charge is sensed by the electrical current that is going on in the 2D layer, because it's so sensitive. And that's used as a possible mapping method.
Yeah, I was just wondering, when you said about these batteries, is it possible, of course, the economics aside, is it possible to replace lithium for electrical vehicles and so on? Is that a possible direction?
Yeah, I mean, I think the storage of charge is essentially what the lithium batteries are looking for here, and graphene, having an extremely large surface area, gives you a natural option to, and that's how the entire battery community went to 2D, because of the huge surface area that you get where the charge can get stored. So yeah, absolutely.
Because lithium is currently in short supply, it is
so that's where the 2D community comes
not so
Correct.
good,
Exactly.
and so on.
Yeah.
So you gave this example of this invisibility cloak type thing.
Yeah.
So where did the actual semi-metallic character of graphene enter in?
It's a very good question. I didn't elaborate that properly. It's a smallness of energy. You see, you're talking about 0.1 electron volt photons. But look at most semiconductors, most materials have got much larger band gap. So there's no way it will be, the electrons, you will be able to, well, I mean, essentially what happens is you can change the emissivity dynamically by simply doping graphene and covering that energy range, which is impossible with most materials that we know.
Thanks. Yeah.
Are there more questions?
So this is about extreme optical response of the heterostructure.
Sure.
So neither of the component, graphene or MOS2, shows that. So how does the band structure of this hybrid system changes, which allow this to have such extreme optical response?
Okay, so that's an interesting question too. I mean, this is what I was trying to stress, the emergence. The emergent property here is extremely sensitive optical response, which is not there either in molybdenum disulfide or in graphene, right? Now here, by putting them together, we are actually not changing the individual band structure at all. All we are doing is that we are transferring charge from one layer to the other. And that leads to the huge response. What happens is that when light comes in, it forms the electron hole pair in the semiconductor layer. But because the graphene is sitting next to the semiconductor layer, the system founds a lower energy configuration with the electron in graphene being transferred electron in the molybdenum disulfide layer being transferred to graphene. And it doesn't come back because there is a surface potential. And then the electron gets trapped and it continuously goes in the circuit and gives you the additional current, whereas the hole remains inside. So there is no change in band structure, but it's additional pathway of charge. That's the secret behind this extremely high sensitivity.
MD material instead of graphene and MOS2, which can also show this property.
Yes, of course.
Yeah.
And that's a very good point as well, because what we can do by changing different materials, we can actually look at different spectral range, because different band gaps of this material will give you sensitivity even in the infrared, which we have seen.
Thank you.
Are there more questions from here? There is a couple of questions from people online, and in particular, there is this question. Would you like to comment or explain a bit about the idea of gate voltage and its how it is used to control the device?
Sure. So this is the gate voltage is essentially like a capacitor, right? What happens is that you have a charge which moves from one end of the sample to the other. And the gate essentially is an electrode which induces charge, or which adds or depletes charge from the channel in which the transport is taking place. So these are connected through a dielectric, which is why it's called a capacitor. And this whole idea of field effect transistor is based on this, where you have got a channel, a source of charge, and a drain of charge, which is coupled to a gate capacitively. This is how I hope that sort of explains it.
Yeah. So the other question is basically, as far as I understand, regarding the relevance of putting the silicon or silicon dioxide substrate. So the question particularly is that why is this used, and is it possible to use alternate substrate?
Of course. Yeah, that's a good question as well. It's just historically important. That is, silicon oxide is, well, I wouldn't say just historically, but there is a scientific reason also. Let me explain both. So silicon and silicon oxide is one of the most commonly used substrate in many electronic systems. The silicon itself is a platform, and there's a very well-known technique in which you can grow silicon oxide as a robust substrate on silicon. But if you look at the original discovery of graphene, people could see single layer graphene even with a microscope, which is one atomic layer thick. And that's not obvious. Why should one be able to see one atom thick material sitting on a macroscopic substrate? Now, it turns out that there's a happy coincidence of reflections and absorption. And it can be shown the visibility of a single atomic layer becomes possible when the silicon oxide layer of a particular dielectric constant of 4 is of approximately 300 nanometer. Okay, so these people were actually experimenting with a 300 nanometer oxide. If they had been experimenting with 200 nanometer oxide, then graphene wouldn't have been discovered. Because you cannot see graphene using a microscope, an optical, conventional, standard microscope that you see in undergraduate laboratories. That itself is enough, simply because the reflection and the interference of the light leads to certain absorption in the visible zone that leads to the visibility of graphene, even if it is one atomic layer thick. So silicon oxide provides that right dielectric constant, which allowed the discovery of graphene in the first place.
Okay. If there are more questions from person audience. Okay. If not, let's thank Arindam once more for the nice talk.
Thank you.